Hello, welcome to my YouTube channel. I am Simanish and this is a course for abstract algebra which is designed for beginners level. Enjoy the course. Please do not forget to share, like, subscribe and comment in my YouTube channel. Thank you. So the first chapter is relation and function. So let's define what a relation means first. A relation between x and y is any subset of the Cartesian product of x and y, x cross y. So for example, we have, let's say, let x be this one, the set containing 1 and 2, and let's say y be the set containing ab. So a relation on set x and set xy be any subset of the Cartesian product. So what's the Cartesian product? Let's first do the Cartesian product of x and y, so which is any set, this one. So we are mapping this, so which is 1a, so we have 1b, so the order pairs, the set of order pairs, whereby the first element is from x and the second element is from y, so which is 2a, we have 2b. So if you take any subset from this set, you know that set is a relation. So let's say this R B, let's say this one, the set containing the order pair 1 and a only. This one be one example. You can have another example, let's say R1, so which contains this order pair 1a and let's say 2b. So know that in the set, this set has 4 elements, so the power set of x, the Cartesian product of x and y, number of this one is to the power of n. So n is the number of elements in that set, so for us it's 4, so this one, so which is 16. That means this set has 16 subsets. So you can take either of the 16s to give an example for the Cartesian product. So there is a case here. So if this x is equals to y, then we say a relation we speak. Let's say we speak of the relation R being a relation on, let's say, x or y, on x. So that means you are taking any subset from the Cartesian product of x with itself. So we have remark. So we know that the Cartesian product of x and y is and the Cartesian product of y and x are not in general the same. Or in other words, the operation here, x and I mean this Cartesian product is not commutative. So for example, if you recall this example here, the example here, so for x cross y, you know that we have that one, and for y cross x, we will take the first element, so that is the inverse of the first one, so which is, let's say, a1, we have a2, b1 and b2. but for x cross y, we had this one, 1a, 1b, 2a, and 2b. As you see, these are not the same. But there may be some cases it can be, both of them can be equal. So the next is, let's define what a domain and range mean. So definition of domain and range of relation R. So now let's recall that. Let's say RB be any relation. Then the domain of R is, which is denoted by domain of R, is defined as, so which is domain of R, which is the set of all first coordinates, set of all x's in X, such that the order pairs x, y is in R. So for some y in Y. So in other words, which is the set of all first components. And the range is the range of R is given by let's say range of R, which is the set of all second components of the order pairs. So which is y in Y, says that the order pair xy is a member of R for some x in X. So this is the definition of domain and range. So let's see an example. For example, recall the example here. And we have this Cartesian product, and let's R be given by the set containing 1a, 1b. So which is subset of x cross y. So what's the domain of R? So the domain of R is the set of all first coordinates. So here the first coordinates are this and this, and they are equal, so we say it's 1 only. And the range of R is given by the set of all second components of the order pairs here inside the set R, so which are this one. So the set containing A and B, or in other words, which is Y. So similarly, you can think of others. So as exercise, try this one, please. And if you have any question, you can write your question in the comment section. So let's say R be given by the set of all, set containing this one, A1, A4, 2, 3, to 4. Let's say 4, 3, and star A. So you are asked to write the domain of R, and so the range of R. Please write your answer in the comment section. So this is remark again. So you have to always remember that the domain of a relation is always contained in X, and a range of R is contained in Y, provided that R is contained in X cross Y. So we are taking the relation, which is subset of the Cartesian product of X and Y. Then if you have this one, we say the domain is subset of X and the range is contained in Y. So like here, as you see in the example here, so the range of R is equals to Y. So there may be also a case that the domain of a relation is also equals to X. So it may happen. Happen that the domain of R can be equals to X, and or can say the range of R can be equals to Y. So there may be a case, it may happen. So another one is, if R is a relation or any subset from X cross Y, I mean the Cartesian product of X and Y, then we can say then R is called a relation from X into Y. So the next one is function. A function or any mapping from X into Y is a function or a mapping from X to Y into Y is a relation, let's say F from X into Y, such that whenever this xy is in F and xy1, let's say where xy1 is in F, then y1 equals to y2. So that means if you have the same first component, you need to have the same second component, otherwise it can't be a function. So that is, if x is equals maps to y and x map again to y1, then to be this f is a function, we need to have an inequality here. let's see an example. For example, here, let's see R be given by the set of this order pairs whereby x and y are in R, say that x squared plus y squared equals 25. So as you see here, this is a relation because it's a subset of the set of the Cartesian product of set of real number to itself. So this is a relation. But this is a relation, but not function. Why? Now let's consider. It's because let's consider two elements here. So we know that now let's have 0, 5, can have 0, 5 and 0 minus 5. So these are two elements of R. So these are in R. But we say to be a function, if the first components are equal, then the second component must be equal. So we have here 5 and minus 5. 5 is different from minus 5. So that's why we say it's not a function. Okay. Try this one also. Please write your answer in the comment section. And if you have any question, please do not hesitate to write your question also in the comment box. Let's have R, which is equals to the set of all x's. Say that x is even integer and y is twice higher than x. So is R a function? So here this x, remember that this x and these are from z, set of integers, z squared. Now we know that a function is a relation. So this comes from the definition. So when you define a function, we say function is a relation satisfying some condition. So, and a function is a relation, so in which x is exactly related to 1 y in y. So when so remember here when we say a relation from x to into y, we are saying that one. So another is, we call this y in y, is called functional value or image of x. Under a function f. So another way of we can write this f as like this, so which is x, and we can substitute y here by using this f of x, so which is the image of x where x is in x. So this is another way of writing function. So we have this notation here. The function f from x into y can be denoted like this, so which is x into y. So this notation signifies the domain of f is equals to x. But we can't say that the domain of, the range of f is equals to y. So, but we can't say the domain, the range of f is equals to y. We can't say that. But in some cases, it may happen. So the range of f can be equals to y. So let's see some properties of a function. So when you say a function is an onto function, so this is a definition. A function f, so this is the shortest form of writing function. So this is only work for me. So a function f maps x into y is onto if for each y in y there exists at least one x in x such that f of x is in y. So that means every element in y has a preimage x. So mathematically you can write like so for all y in y there exists x in x such that f of x is equals to y. So any function that satisfies this condition we call a function is an onto function. So you can take an example. Let's say f of x which is equals to let's say x, like an identity function. So this is where x is element of A. So this is an identity function, so it's obvious to show that this is an onto function. Try for yourself. What about this one? F of x, which is given by, let's say, x squared, where x is element of R. But let's consider f, which is a map from Z to set of rational number defined by f of x, which is equals to x plus 1. So is this function an onto function? So try this one as exercise and please write your answer under the comments. So let's do this one. So here, now remember that this is a function, we know. You can check also if it's a function or not. So this is another way of checking whether a given relation is a function or not. So that is, you can take two equal elements. So this is like, you can say, rule to show function or to check a function. So that is, you say, let's say x is equals to y, has to imply that f of x equals to f of y. Now any relation satisfying this thing, we say it's a function. So let's check for us using this one. So here, now we have, let's say, x is equals to y, or another way to say this is to show it's a function, or to check function, we say, in other words, we say well-definedness. So let's suppose that x is equals to y. Then if you add both sides 1, you get x plus y, x plus 1 equals to y plus 1. They're the same because they are integers. So which implies that this is the same as f of x, which is equals to f of y. So that means it's well defined. That means it's a function. Therefore, f is function. So now to see it's onto, now let's take any arbitrary element from this one. So let's, for example, half plus 1. So this is element of Q. But as you see here, half is not a member of Z. Therefore, we say this F is not onto. Now, the second one is one-to-oneness. So we say a function f is said to be one-to-one if and only if for x1, x2, in the domain of f with x1 different from x2 implies that f of x1 is not equals to f of x2. Or we can rewrite this one as a rule. So to check one-to-oneness, so you start by supposing f of x1 equals to f of x2, and if you show that x1 equals to x2, then you are done. So this is one-to-oneness criteria. For example, now let's see. Let's say f of x, which is equals to x squared whenever x is elements of, let's say, z, the set of integers. So this is, that's a function. Now let's show that f is one-to-one function. So to show it's a one-to-one function, it's not a one-to-one function. To show, now we have, let's first check the well-definedness or a function being a function. So let's suppose x1 equals to x2. Then if you square both sides, now it keeps this one. So which implies that x1 square, which is equals to x2 square. So this implies that f of x1, which is equals to f of x2. Therefore, we say f is well defined, or it's a function. Now, how about the one-to-oneness? Now let's suppose that f of x1 equals to f of x2. Now that means f of x1, according to our definition, which is x1 square, which is equals to x2 square. This implies, does it implies this x1 equals to x2? No, because you can take minus 2 the whole square, which is equals to 2 square. So that is 4 equals to 4, but minus 2 is different from 2. Therefore, we say f is not one-to-one. So, therefore, to sum up, so we say a relation R is any subset of the Cartesian product of x cross y, and we say any function is a relation but not converse. Again, we say, now this is the criteria to show functionness or well-definedness is this one criteria. So the first one is if we say x is equals to y, and if you show that f of x, which is equals to f of y, then this is a criteria for well-definedness or to show function. the relation is a function, and you have f of x equals to f of y implies x is equals to y, then this is a criteria for one-to-oneness. And from the definition of one-to-oneness, we have for every x I mean for every y in y there exists an x, which is a member of x, such that f of x has to be equals to y. So these are some points you need to remember under this one. Also, we say that the domain of a relation a relation R, which is the set of first coordinates, say that this xy is in R, where for some for some y in R, similarly for the range of R, which is y the second component, which is whereby the order per xy is in R, for some x in this is in y and this has to be in x. So we are considering, remember that we are considering R is taken from x to y, but if you consider from y to x, then it should change.